Hey there, my fellow intellectuals. Today, you're in for a treat. You're going to see me solve my most hated problem, as an undergraduate physics major. Now, a little bit of context. This problem can be found if you have a copy of Griffiths Electrodynamics. This is the 4th edition, and I believe the number of this problem is 226, so chapter 2, problem 26. And this is my most hated problem as an undergrad. It may not have been the most hard problem I ever had to solve, but this problem stuck with me the first time I ever saw it. It just traumatized me, and I couldn't stop thinking about it. I didn't get it right on the homework assignment either, and it wasn't until like months later that I actually solved it with the help of like software like Mathematica to do some integrals. And it was only until recently I was able to do this problem completely by hand. And that's what we're going to do today. So for any of you aspiring physics students who will ever come across this problem, you're welcome. So let's begin. So how do we even start here? So the problem is essentially you have this hollow cone. It's like an ice cream cone without the ice cream on top, which is kind of sad because when you think of ice cream, you think of yummy things and, you know, something tasty and delicious, not something so vicious and demoralizing to your just intellect. But nonetheless, we will solve it. So we want to find the potential difference between points A and B on this cone, which happens to be a right circular cone. And what that means is that for every height z, so let's say you're at a height z here, and you're at a radius r on the cone. For a right circular cone, that just means z is always equal to r on this cone. So not only is the radius at the top supposed to have a value of big R, but after all I'm done erasing here, I can say that the height of this cone is also R. So that's what defines a right circular cone. And we know that it has a uniform surface charge sigma, so we just care about the charge on its surface. So to start this problem, I propose we start with the potential formula. We just say V of R is equal to 1 divided by 4 pi epsilon 0. We integrate the charge density, R prime, dV prime, over script R. But remember, we are only dealing with a two-dimensional surface charge density sigma here. This is two-dimensional. What I wrote down here is the three-dimensional case. So for the two-dimensional case, what it's going to be is, let's just write it over here. 1 over 4 pi epsilon 0. We're going to have sigma of R prime dA prime over script R. Okay. So that is the basic equation for the potential for an arbitrary source of charge as found in Griffiths' book. Remember that the script R vector is just equal to the field vector minus the source vector. Right? So that's the definition of that. So what I propose to do is let's find the potential at A. So find V of A and then find V of B. Okay? That's what we want to do. So first off, we're going to find V of A, then V of B, and then we take the difference between the two. So that is my strategy for this problem. And so how are we going to find V of A? Well, we need to represent the different values or the different variables in this integral. So first off, we can say that sigma of R prime, just switching color here, is going to just equal sigma. And now we have to be careful about this dA prime. So this dA prime is going to be a little bit tricky. I'm not going to focus on it quite yet. We'll just look at what script R is first. So let's look at script R. So if we focus on script R, so sigma here. So if we focus on script R, it means we just pick a point on this cone and we'll represent the coordinates of that point, and just we're pretty much just going to find a vector that points from a point on the cone to the point at A, right? So that's what script R is going to be. So let's say, for example, I pick this point right here on the cone, and the script R in this case will be this length right there. Okay, one way to think about it to make it easier for us, let's just imagine we center the cone. So center the center vertex at 0, 0, 0. So essentially A is at the origin. So A is at origin. Okay, so this is going to be my script R. So the source point is right here, the field point is at A, and this is the distance between those 2 points. Okay, and to represent that a little bit more clearly, we can think of it as, we can make a triangle here where this height here is Z and this part up here is R. But remember, this is a right circular cone and that Z is equal to R. So we can actually just write this as, let's just write Z here. Okay, so cool. So in this case, if you notice, we have a triangle in this cone here that I have in blue, and the triangle looks something like this. I have Z, Z, script R. This tells us if this is a right triangle here. From this relationship, we know that script R is equal to the square root of 2 times Z. Right, that's just a 45, 45, 90 triangle, thanks to the right circular cone. Okay, so I have what script R is. Now I need to figure out how do I represent my dA here. So how do I look at this dA prime? Well, one way to think about it is, imagine we're at some point on this cone, like up here, and we're going to cut this cone into little strips, and I'm going to draw what I mean. So example, let's start here, and we draw a little nice circle of radius Z, and then we take this portion up here, right? So we're making these nice little strips on the cone like this, right, in red here. So that is going to be our differential area element. So this red part is our dA prime. Okay. Now, how do we think of this dA prime? Well, I'm going to go down here a bit. dA prime, we can think of that as 2 pi Z. Now, why do I think of it like that? Because remember, we have the 2 pi Z coming from the circle on the bottom of that cone, and we have to multiply this by the slant, right? This is not a perfect cylinder, right? This is a cone. So if we had a cylinder, so if cylinder, I'd write dA prime is equal to 2 pi Z dz, right? Because we have something like this where the bottom circle and the top circle have the same radius, right? But this is not the case. We don't have a cylinder. We have a cone. So for the cone, we need to write dA prime is equal to 2 pi Z d script R, right? And remember, script R is this variable right here, which is just going along the direction of the surface of the cone. And we have to relate what the script R, the differential script R is to the differential dz. So we need to relate, d script R with dz, right? And how do we do that? Well, one way to think about it is we can draw this this differential area, this slice. So imagine here's the smaller slice. Oh, sorry, that's the bigger slice. Here's the smaller slice, and this has the radius Z. And here is the d script R, right? So this slant right here is the d script R. What we can imagine is, we just made a dotted line right here. I'll draw it in blue so it's easier to see. Imagine we just made this a cylinder, right? Imagine we compare what the differential area would be like to the slice of a cylinder, right? So imagine that instead of having a a slant here, we have just the normal cylinder height. And one way to like think about this is kind of hard to see, but essentially we have this little triangle right there. It's kind of hard to see, so I'll blow it up. So we have this triangle right here. I have this blue side, I have this red side, and I have this red side right here. Now the nice thing about this is that this is a right circular cone. So I said that this blue side, let's imagine that it's like a cylinder in the sense that the radius of the top circle is the same as the radius of the bottom circle. Well then, this is just a differential dz right here, okay? So that's dz. Remember the red slant is d, maybe I'll write it in red again so we keep things consistent. We write it as d script r, and how do we figure out what this top leg of our triangle is? Remember, this is a right triangle right here, okay? And if we want to figure out what that top leg is, the easiest thing to do is just realize that this is a right circular cone. Remember that changes in z correspond to the same amount of changes in radius, right? So this is a right circular cone. Remember, I said that z is equal to r. So if z is equal to r, that means if this is a dr right here, dr is also equal to dz. So, great. So with using those two pieces of information, we again have a right triangle. Remember, we had like the same right triangle above with z's and with, you know, non-differential z's and non-differential r's. But here we have dz, dz, d script r. And so we know that d script r is equal to square root of 2 dz. Okay, so that was a mouthful. We finally got our differential area element, right? So our differential area element, dA prime, is equal to 2 pi z d script r, which is equal to 2 root 2 pi dz. So that we finally have our differential area element, and we are going to now finally do some integration. So we're going to use the formula right here. We're going to use this formula right there. And let's just write it down one more time. So I'll write it as v of r. Oops, don't go sliding away from me now. Oop, my colors are showing. Okay, so v of r is equal to 1 over 4 pi epsilon 0. Remember, we have the integral from, well, we're not integrating quite yet, so I'll tell you the bounds later. So remember, we have a sigma, we have a dA prime, but that dA prime is just 2 root 2 pi dz. And we divide this by, oops, sorry, I forgot the z here, my bad. There's a 2 pi z dz, right? So there's a z right there, there's a z right here. Okay, and what you call it? The script r in the bottom. So we have a script r in the denominator, and we found that script r is just root 2z. So we have root 2z in the denominator. And where are we integrating from? Well, remember, we're just going to integrate in the z direction, right? So z, if we go back to the cone, I'm sorry, there's a lot of going up and down, but remember that z goes up to a height of r, right? So remember that the radius is r, but this is a right circular cone, so that means the height in the z direction at the top is also r. So we're going to go from z is equal to 0 to z is equal to r. And we can cancel some things. There's a z in the denominator and the z in the numerator. There's a root 2 and a root 2 canceling. There is a pi canceling with a pi. There's a 2 canceling with a 4 to give a 2 right there. So a lot of canceling, but this just reduces to sigma over 2 epsilon 0 integral 0 to r. We just have dz. There's nothing else left in the expression. So this just gives us a value of r. So at the point at v of a, so sorry, this was v of a. V of a is equal to sigma r, because this is r, sigma r over 2 epsilon 0. Okay, so check. That is the first part of this problem. And now we will go on to the more challenging and the more difficult part. And I'm smiling because I just know we are in store for a really long adventure in front of us. I know it's already been a long video, and it's about to get much, much longer. So if you've made it this far, kudos to you. We're going to keep going, and we're going to do this integral by hand.